Hey, good morning, y'all. Let's see, when is our exam? In 2 weeks, yeah. So we have all next week, and then we'll come back on the 19th for an exam. Let's aim to have a quiz on the 14th, okay? I'm not sure what the content of that quiz will be, but we'll have a quiz on the 14th. It'll probably be, I don't know what it'll be. We'll have to decide. It's sort of depends on what kind of, huh?
Fun.
Because I want the quiz to cover the context on the exam. It might just be sort of the second half of this chapter. Yeah. Yeah, I'm not sure. Well, don't write that down. I'll let you know next week. But I've been definitely reading through chapter 2. That's what we're on now, right? Chapter 2?
Yes.
Yeah. And then the test will cover chapters 0, 1, and 2. So that's what we're aiming for.
It's on the 19th.
On the 19th, yeah, that's right there, the little blue grayish thing. All right. Y'all excited about the exam? The quizzes, y'all been doing pretty well on the quizzes. Huh?
I've been missing like 2%.
2%?
No, I've been missing like 2 or 3.
Oh, well, quizzes are a place to mess up. But the exam, you don't want to mess up the exam. Okay? Y'all know what to do to study these days? Every night? Read the book, read the notes, work through the old fast quizzes. That's what y'all need to be doing. Just 20 minutes a day. Everybody has 20 minutes in a day, right? Yes, you do. Oh, no, you don't have to do it all at once. Just do it a little bit at a time.
Yeah, that's every.
All right, Joey. All right. So we talked about last time, I sort of showed you that video of Veritasium about the straw. I just want to explain that in a little more detail. Let me show you a barometer. I drew a barometer like this, where I have two pressures. I have a pressure here and a pressure here. And if I have a big pressure here, it pushes down and pushes the fluid up. You follow me? I have a really big pressure here and a smaller pressure here. And so this side is able to push the fluid up. And that's how a straw works. This sort of duck-like fella, he creates a low pressure inside of his mouth, and the higher pressure, which is the atmospheric pressure, pushes the liquid up into the straw. Okay? Let me reiterate that. I have a pressure over here that's big. I have a smaller pressure here, and that's why I have these two different levels. I get this extra little bit over here. And then the pressure that's causing that is proportional to this H, right? P is equal to rho times G times H. We saw that last time, that if I have a height of a column of fluid, that the pressure at the bottom of that column of fluid is going to equal to rho times G times H. And we get that from the weight of the fluid, all compressing down on that one particular point. Okay? Now, a barometer really looks like this, or a sketch of a barometer. You have some dish with some liquid in it, mercury, for example, and then you have a tube that's inserted into the dish upside down, like this. The tube is a vacuum, perfect vacuum, so there's nothing in it. It has no pressure at all. And then you get this atmospheric pressure that pushes down onto the surface of the liquid, and it pushes that liquid up into the tube. Now you still got a little bit of space up at the top. Now if this is 1 atmosphere, and if I'm talking about mercury in this tube, right, this, not HQ, Hg, excuse me. If I'm talking about mercury, like in the blood pressure deals with a little column of stuff that goes up and down, that's mercury in that, or like you have in a thermometer often, you have a mercury thermometer. But if I have mercury in that, which is a really dense liquid, then the height of this column is going to be 760 millimeters. However, if I have a substance, say, I don't know, water, or Coke, or wine, or something like that, they all have about the same density. Does water have less density or more density than mercury? smaller is less. Right. The density of water is a lot less than the density of mercury. I think mercury is like 13,600 kilograms per cubic meter. So if I had a cubic meter of mercury, about this much mercury, it would be 13,600 kilograms. A person's about 70 kilograms. So it's really heavy, mercury. Whereas water, if I have a cubic meter of water, it's going to be about 1,000 kilograms. The density of water is 1,000 kilograms per cubic meter. So a lot more dense, mercury. So if this is filled with water or Coke, then the height of that column is going to be 10 meters. I told y'all this last time, that the very first barometer, what was his name? He was Italian, I think. Something Jelly. Articelli? That's possible. Anyway, some Italian guy that built the very first barometer, he tried to use lime, but he had a lot of trouble because the column was just so high, and it was very difficult to create a vacuum at the top of a column that's so high. That's why in the video, it was really difficult for him to suck up water up through he did 6 meters in the part that we saw. But later they go and they try to do a 10-meter straw, and they're not even close. He said it felt like it was like they was trying to suck his face into the straw. All right? So 10 meters then is the theoretical limit on how long a straw can be. That if you have a 10-meter straw, and if you can create a perfect vacuum, have zero pressure inside of your mouth, then the atmospheric pressure will push the liquid up into your mouth. Okay? Y'all follow me on this? Yeah? You're like, this is another good game for when you're out with your stupid friends, when y'all go out and they're all drinking or getting stupid. You know, you can do the thing with your leg and you can make a lot of money off of them, and then you can give them a 10-meter straw and tell them to try to drink this straw. Like go up on the second floor or third floor, the fourth floor, 10-meter, a 30-foot straw. Okay? I think that should be like I mean, I don't do drinking games, but that should be a drinking game, I think. Like people do, I know y'all don't do this, but when people do like, what do they call it when they turn you upside down? A keg stand. But instead of that, like we'll get rid of that, and we'll instead drink through a 10-meter straw. Like we'd have much smarter people. You wouldn't be. But you couldn't really drink out of it. All right, let's try some of these questions. The one on the left first. Oh, this was from the quiz, I think, wasn't it? Wait. It was a good lesson for me because I'll make the math as simple as I possibly can. Very, very simple numbers on this test. We'll do the one on the left here. All right, let's stop at 35. 35. Awesome. Or maybe I should put that exact question on the test, right? Yeah, right. Let's see. Two atoms walk into a bar, and one of them says to the other atom, "Hey, I think I've lost an electron." So are you sure? Yeah, I'm positive. Yeah. That's an old one, isn't it? Let's try this one on the right then. I think this was on the quiz too, wasn't it? Oh, yeah. Look at that. Huh? Yeah. They were from old tests. Usually on the reading quizzes, those are usually old questions that I pull from the old reading quizzes or tests. They're also in the textbook, so if you read the textbook, you'll get them. The exams are often new questions. It's sort of a mix of old and new. Look at you people. You are awesome. You're amazing. You're perfect. Jillian?
I have a question.
Oh.
So for the first question, the book says it's 340.
340?
But it does say like it's a percentage of like
For this one?
the weight. The book can use. I just I just want clarification. Yours is correct.
Okay,
It's
well,
good.
yeah, the way that we do this is our pressure is force over area, and that's the force is 180. Like that's your weight, right? And it's important that you stand on one knee, because if you stand on one foot, because if you stand on 2 feet, then it splits it between your 2 feet. So if I stand on one, then all of that 180 pounds goes on my knee joint, and I have an area of a half square inch. So that's 0.5 square inches. So that is 180 over a half. That's equivalent to 180 times 2. And that's equal to 360 pounds per square inch, or PSI. Okay? I'm not sure. I think the book was maybe dealing in another unit or doing something a little bit different.
It might be something different.
Yeah.
Like clarification.
Okay. Yeah. All right, let's look at Pascal's principle. Pascal's principle says when pressure is applied, to a fluid in a closed container, that pressure is felt throughout the container. So if I think about a piston, say a piston looks like this, and it's filled with some fluid. Actually, it has to be a special type of fluid. It has to be an incompressible fluid. So if I have this container filled with an incompressible fluid, which you know, fluids are anything that flows. An incompressible fluid is a what? A liquid. So when I say incompressible fluid, I'm really thinking really any liquid will do. Water, hydraulic oil, really anything. Any kind of liquid is incompressible. So if I have this piston and I push down on it with a certain force, the piston has a certain area, so the pressure that you're exerting on this is that force divided by that area. So for example, if this is 100 newtons and this is, I don't know, 2 square meters, then the pressure would be 50 pascals, for example. I'm pushing in on 100 newtons, my piston has an area of 2 square meters, then that pressure, which is 50 pascals, is felt on every side of the container. And at every point in that container, I have 50 pascals of pressure. We sort of saw that with tension, right? Tension's different, but it's a similar idea. That if I apply a force to one point, that it's distributed all the way across. So for an incompressible fluid, if I apply a pressure to it at any point, that pressure is felt throughout. Because it's incompressible. If it was compressible and I applied a pressure to it, it would just squish in that one side. But since it's incompressible, if I push on it, that whole pressure is felt throughout. That's Pascal's principle. And it's kind of useful, Pascal's principle, because it allows us to build things like hydraulic lifts, which we use a lot, actually. We use them to lift cars, of course, right? When you go to the tire shop and they lift up your car, that's a hydraulic lift. Often the jack that you have in your car is a hydraulic lift. Sometimes it's not. Sometimes it's a screw type machine, like a simple machine. You know what I'm talking about? You'll see the little screw you screw, but some of them are hydraulic. Those are the kind where you do like this. You know what I'm talking about? The jacks like that. Opposed to the screw type where you spin it. So hydraulic lifts, use them to, if you go to the barber shop, just to the barber shop. Anybody? Nobody? the hairdresser. My wife cuts my hair. We don't have a barber's chair, but I've told her that we need to get one because she cuts everybody's hair in our family except for her own. She's the only one that goes to the salon. Because I don't know if you know this about me, but we're kind of cheap. Like we're not cheap. We're very careful with money, as Elaine said. No Seinfeld? You don't like Seinfeld? You've probably never seen it, have you? You ever seen Seinfeld? Yeah. Anyway, I told her we should get a barber's chair. And they have a hydraulic lift. When you step on the pedal, that's what it does, is it has a hydraulic lift. You use them to lift people in the hospital, wherever. But a hydraulic lift, a cartoon version of it, looks like this. I have a pipe that's filled with fluid, incompressible liquid. I apply a pressure over here, and I get the same pressure over here. Right? That's Pascal's principle. So whatever pressure I apply over here, I'm going to get the same pressure over here. But notice how I drew it. That this side has a really small area, and this side has a really big area. Now I know that pressure is equal to F over A. F over A. So if I were to draw this, I'm going to sort of write the equation, but with the letters representing the size of the variables. So if A over here is small and A over here is big, the area on this side is really small. It's just a small value. But the area on this side is big. Then how do the forces differ? I know the pressures have to be the same, but if I put in a force here, will it be bigger or smaller on this side? It's going to be bigger, right? So if I put in a small force on the left-hand side, because of Pascal's principle that pressure remains constant, I get a big force on the other side. So for example, if I put in, I don't know, 2 newtons over here, and I have 2 square meters, that means my pressure was 1 Pascal. That was the pressure that I exerted on the small side of the hydraulic lift. Now let's say that my area over here is 4 square meters. That means that my force is going to be, what? 4. It's going to be 4 newtons. So because I doubled the size of the area, I also doubled the size of the output force. All right? We'll see this a little bit later in the next chapter as it regards to the work that you do. But I'll tell you right now that if you want to lift something a small distance on the right-hand side, like if you want to lift your car, you really want to lift your car about 6 inches up off the ground. But have you ever used a hydraulic jet? How much do you have to move this thing to lift it just 6 inches off the ground? You got to do a lot, right? That's why you go. The handle goes up and down a bunch of times. And we'll talk about that next chapter, how the works are related, that we're not losing any energy. But for now, just think about Pascal's principle. We'll see it in the heart, too. The heart applies pressure that is felt throughout the body. Although we'll see that the body is a little bit different, or it's not different, but because your body changes height, that you'll have different pressure readings for your blood pressure. Right? Where are you going to get a higher pressure reading? Here or down at your feet? Well, you get on your arm. Well, yeah, because you're closer to your heart. But I'm getting to the point that if I have all this fluid in my body, right, there's a certain amount of pressure just due to the weight of the fluid. So if I take my blood pressure down here, I have to consider that I have all this fluid sort of bearing down on that, so that increases the pressure. Anyway, the heart applies pressure that is felt throughout the body. A baby pushes on its mother's bladder. Your book talks about each of these. And when a baby pushes on its bladder, it kicks you or whatever, and that applies a pressure, and then that's felt throughout the entire bladder. We'll talk about the bladder later. It's kind of interesting. All right, there are three different pressures: the gauge, atmospheric, and absolute pressure. The gauge pressure is the pressure reading on the gauge. The atmospheric pressure is the pressure due to the atmosphere. And the absolute pressure is the sum of the gauge and atmosphere pressures. ATM is atmosphere. So if you have a flat tire, or really, you probably don't want to think about yourself, but if you have a friend that has a flat tire, you ever had a friend that has a flat tire? Yeah? Yeah? Like when I was a kid, my brothers, I was the first person in my family to graduate high school, ever. Like ever in the history of my family. I had two older brothers, they both dropped out of school because they hated school. And they hated school. They would skip school a lot. And one of their tricks, we lived way out in the country, and we had to drive into town to go to school. One of their tricks was to do what? Get a flat tire. Right, so you go out in the morning, you let all the air out of your tire, and then you go out there and you try to go to school, and you're like, oh, my tire's flat, I can't go to school. And so then you don't go to school. But if you ever have a friend that has a flat tire, go up to them and say, hey, your tire has a lot of pressure. It has like, I don't know, 100,000 pascals of pressure. Because it does, right? Like even though there's no pressure in it, or even though it's flat and laying on the ground, there is a pressure in it, just like there's a pressure here of 100,000 pascals, or 100,000 newtons per square meter. And that 100,000 is the atmospheric pressure, the pressure due to the atmosphere. But then the pressure in the tire, it has like this extra pressure. And that's what the gauge pressure is. That's your 35 psi that you put in your tire, 30 to 35 psi. And then the absolute pressure would be the sum of those two, the 35 plus the 1 atmosphere of pressure. Okay? Usually all we're interested in is the gauge pressure, because that just tells you the pressure that's above what atmospheric pressure is. So the absolute pressure, if you want to think about this in terms of a formula, the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. Is that on your equation sheet? I don't think it is. It's not usually a formula we use. No, they're not on there. Okay? So those are sort of three different pressures. Look, I have a video I want to show you. I think I still have it. Let's take a look. I'll look for it. Maybe we'll watch it next time. It's not going to be on the test. It was just sort of for your own interest. All right. Let's look at the ideal gas law. Consider a container of gas. A closed container. And in that sentence, what I'm saying is that a container has a certain volume. So I'm considering a certain volume of gas. And you know, a gas is different from a liquid or a solid, that when you put a gas in a container, it doesn't just sit in the bottom of the container, it fills the entire container. So regardless of how much gas you have in a container, whether it's just, you know, a little bit or a lot, it's still going to fill the entire container. So a closed container of gas has a set volume. If you add gas, the pressure increases. If you raise the temperature, the pressure will also increase. right, so if I have P is pressure, V is volume. That's just based on your container. But in this case, we're assuming that since it's a container, that the volume is constant. So I'm going to write that in parentheses, that the volume in this case is constant because I'm just considering a particular container. T is the temperature. And then also N, lowercase n, is the amount of gas. Y'all have had this in high school chemistry, I'm sure, right? The ideal gas law, I'm talking about. N is in moles. We're not going to convert moles, kilograms, any of that business, but I just want you to understand the ideal gas law and how it applies. And then there's a constant too. We're not going to worry about the constant. So the ideal gas law describes the relationship between these variables. P times V is equal to N times R times T. Don't worry about R, it's just a constant, but you've probably seen the ideal gas law. Yes, ideal gas law? In high school, maybe even here at Nichols, chemistry or physical science. So it says that if V is constant, if N goes up, that means that P is going to go up. And if T goes up, that also means that P will increase. If N, the amount of gas, I have a certain container of gas, if I stuff more gas into that container, the pressure goes up. That sort of makes sense to me. Sort of makes sense to you too? That if I just add more gas to the container, the amount of pressure is going to go up. The molecules actually get closer together, they start bumping up against one another more, and that increases the pressure. So the ideal gas law talks about the pressure due to the interaction of molecules. That might have been on your quiz. Was it? Or it was an option anyway. What's that on your quiz? I don't think so. I'm trying to put it out of my mind. And then also, if I keep the same amount of gas, but I raise the temperature, then I make the molecules move more and faster. And they bounce into one another more, and then that raises the pressure of the gas. Oh, look, I have this. Turn on the lights. Katie, you want to turn on the lights? You think I said Katie? Oh. All right, so look, this is a plate. Flat gas. Is there a flat gas somewhere? Oh, you're using it. That's okay.
I can get out of it.
No, that's all right. I'll do it up here. You'll be able to see better anyway. All right, so I have some matches. I just cut them off so they're short. And I have a cup I'm going to put over it. I'm going to light the matches. I'm going to have some water on the dish, and then I'll put the cup over it. And well, let's talk about sort of what's going to happen and why it happened.
It's gonna stop.
Don't tell them, but that's like giving the punchline for the joke. D? Y'all didn't hear what she said, did you? Good. Whoop. All right. So, if I light the matches, what's going to happen to the temperature around the matches? It's going to increase a lot. Like, they're really hot. I don't know if you ever touched a burning match, but they're really hot. And so I'm going to light the matches here in just a moment, and then I'm going to put the cup on top of the matches. And then the temperature inside of the cup is going to increase a lot, right? And then what's it going to do when the temperature increases inside of the cup? The pressure increases, right? Ideal gas law. If T goes up, that means that the pressure goes up. Now the amount of gas that we have stays the same, mostly right at first anyway. And the volume stays the same, well, mostly right at first. So the pressure is going to increase. And look, this is kind of like a barometer with the thing that's upside down in the dish of water. What happens if I increase the pressure inside of the cup? It's going to push water outside of the cup. So a little bit's going to come out. And then what's going to happen to the matches inside of the cup? Right, they're just going to go out, right? Because they're going to eat up all the oxygen that's inside of the cup. And then what's going to happen to the temperature? It's going to drop. And then what's going to happen to the pressure? It's going to drop. And then what's going to happen to the water? Because look, all of a sudden now I have a low pressure inside of the cup, but I have a high pressure on the outside of the cup. What? Yeah, that's it. So we'll see. What did you say? Okay. All right. Y'all ready to watch? Can y'all see okay? Rue, can you see? You see? It's kind of nervous. Does it make y'all nervous? It doesn't make you nervous? Oh, there we go. Look at that. Y'all see the water? It's kind of nasty yellow water because of the clay. Can you see? So remember, again, when I light the match, it just heats up the space around it. You put the cup on it, and with the temperature going up so high, really, really hot, the pressure goes up, and then that forces the water out. Okay? And then the matches go out, and the temperature drops, and so you get a low pressure. And so then you have a low pressure inside of the cup, and a high pressure outside of the cup, and so the atmospheric pressure, just like in the straw, pushes down on the water here and pushes it up into the cup. And so now we have a perfect system. Like we have a low pressure inside of the cup that's the same as the pressure outside of the cup. And that's really what nature wants. They don't want this pressure differential. Now, can I make it to the door without spilling? Hopefully. Alright, so that's the ideal gas law. Well, Boyles law is just a special case. When you're in chemistry, you probably studied Boyles law and Charles law. I want you to understand Boyles law because it relates really well to breathing. Boyles law is a special case. If if N and T are constant, then PV is equal to a constant value. So all we're saying is that PV equals nRT, right? If we say that this is constant and this is constant, the amount of gas that you have and the temperature of that gas, then the product of the pressure and the volume, that has to be constant. And a good example of that is breathing. Y'all breathe for me? Go ahead and breathe. When you breathe, really all that you're doing is you're changing the volume of your lungs, right? Your lungs don't actually change volume because they're sort of sacs that sit inside of your chest. But your diaphragm changes the shape of your chest cavity, and then that allows your lungs to either get big or small. And so when you breathe in, the volume of your lungs do what? They get big or small?
Big.
They get big. And if the volume gets big, what happens to the pressure inside of your lungs? It decreases. And if you have a low pressure inside of your lungs, what happens? Right, because you got high pressure out here, low pressure in here, air rushes in. Just like with the thing here where I had the high and the low pressure differential. Come on, everybody. All right, big lungs, low pressure, air rushes in. But then when you exhale, can I exhale? Are you exhaling? You are. Thank you. When you exhale, what happens to the volume inside of your chest? Decreases. And if the volume goes down, that means the pressure goes up. And then that forces the air out of your lungs. So that's a great example of Boyle's law. So let me just sort of draw a picture. I'll just do it like this. Big volume, small pressure. So this is inhaling. And when I have a small pressure, I have a high pressure out here, and so the air rushes in when you're inhaling. That's a picture of your lung. And then here, in my notes, I have a picture of a guy, like with his lungs, but it looks a lot like the guy that was on the straw, so I'm not going to try to draw it because he sort of looks like a duck. In this case, let me draw it smaller actually. This is exhaling. I have a small V. So I have a big pressure. Out here I have a low pressure. And so that means that the air is going to go out. This is exhaling. Yeah, we'll see that later. Okay. Pressure in solids. Solids can also experience pressure. They're a little bit different. We don't think about them in kind of the same way as we do when we think about how gases experience pressure, but it's a lot the same. And this is kind of like the problem where we did with the knee joint. So which exerts a greater pressure? Remember, pressure is F over A. A lady on high heels. You ever wear high heels? High heels have a tiny little step on the back. Like maybe it's, I don't know, a half a square inch or so. It's not very big. So if I have a high heel with an area just for the back of a half of a square inch, and if the weight, the force of that's going down onto the heel of that shoe is, say, I don't know, like 120, 130 pounds, then that means that I have a pressure equal to 240 psi. But if I have like a football player, now let's say that the area of his foot is, I don't know, 12 inches by a few inches, say 30 inches squared, and if his weight is 200 pounds, then the pressure in this case, even though he has a much bigger weight than the lady in high heels, then the pressure is, well, 200 divided by 30, and that's approximately 7 psi. So there's a much bigger difference, there's a big difference between the pressure, say, a lady in high heels and a guy that's just standing on one foot like that. That's why if you've ever had a lady in high heels, ram their foot ram their heel into your toe, that it can be quite damaging because you have such a small area and you don't need a really big force to make that harmful. It's the same, right, with a push pin? Like I can take a pin or something like this and push it into my arm all day long, and it's not a big deal at all, right? But if I have a push pin and I try to do that, that's going to cause a lot of harm to me, correct? And the reason is because the pressure is so much bigger. The area is a lot smaller on a push pin. That's a tiny little area on the end of that push pin. But a regular writing pin is like nothing. Okay? Try it with your friends. Tell them, hey, let's do this with a push pin and then like with a writing pin and see what they say to you. Okay? All right. Y'all still do this at concerts? When you go to concerts? Hold out your cigarette lighters?
Or your phone.
Huh?
They throw away phone.
Your phone, right? Yeah. And y'all don't smoke anyway. Most do don't. Yeah. That's good. It's good not to smoke. We can also talk about pressures causing stress and strain. You're not going to see this a whole lot. Your book goes into it more. I just want you to know what stress and strain are. It's kind of important when you're talking about bones breaking, because you'll talk about the stress that causes the stress. That's sort of the action. And then the strain, that's the reaction. So the stress is the pressure that you apply. And then the strain is going to be how does the material respond. So pressure in solids cause stress and strain. The stress causes a strain. Engineers deal in this a lot too. They talk about stresses. You have some stress. It is a force per unit area, and then it causes some strain. And the strain is a deformation. The simplest that I can think of is, you ever use those bands, those exercise bands? Right? The stress is the area of the band, or the force that you apply to the band divided by the area. And then the strain is how much do you stretch that band. Okay? So that's sort of the simplest in one dimension, a stress and a strain. But you can talk about stress and strain in multiple dimensions, in 2 and 3 dimensions. If you go into graduate school for PT or kinesiology or athletic training, you'll probably get into stress and strain more. If you exceed the elastic limit of a material, then that material will break. And I think that your book talks about this in greater detail, but that's, as far as we're concerned, for the test, that's all that I'll ask you about. In general, I've said this before, but let me reiterate. The quizzes, everything in the book is open, but it's sort of just, I try to think the big ideas. But on the test, I limit it to what we cover in the notes. So sometimes there are topics that we don't cover in the book, or at least not as in much detail as the author does. And so you won't see that extra detail in the test. So the notes are a good place to start for the test. When you exhale, your chest cavity gets wet, and this causes a what pressure? All right, let's do about 5 more seconds. We'll stop at 28. Good. C is right. Hey, knock knock. Interrupting pirate. Arrgh. Oh, what did y'all put? What was the answer? Oh, C is the right answer. Yeah, when you exhale, your chest cavity gets smaller, and then that causes a high pressure. Yeah.
We wrote that there's alternatives like in the book, but if we took the test.
Oh, yeah, of course. But the quizzes are open,
Yeah.
right? It's not, there's like three quizzes sometimes. Listen, if you're on your test, this isn't cheating. And you get a question like this, you go. That's not cheating. I don't think that I could tell you don't breathe on the exam. Don't think that would fly with my boss. As one descends to a greater depth in a liquid, what happens to the pressure? Looking at this one right here. All right, let's stop at 20. All right, awesome. That is right. Think about the swimming pool. You go to the swimming pool, and you go over here, and you try to go to the deep end, all the way to the bottom, or you lose your goggles down there, and you have to go down to the bottom. What happens when you go to the deep in a pool? Your ears pop. It hurts, right? And not only that, but you can just, I can feel the pressure just pushing down on me. There's a lot of pressure, even just going down about 9 feet. Yeah, but there it's a different kind of pressure, because in the pool you're going to high pressure, but in an airplane you're going up. You're going into what? Low pressure, right? They try to equalize it. They try to keep it stable for you as much as they can, but you still get a lower pressure when you're in an airplane. And that's why, too, if you take a bag of potato chips onto the airplane and you get up to 30,000 feet or wherever they fly, you look at it, it's all blown up. You ever seen that? You ever taken it? Yeah, try it. I think that they sometimes have packaging that doesn't do that. But sometimes some potato chips will do that. I think Lay's do it. All right. So the pressure increases. So let's try this one on the right. This is kind of like a barometer. But what I have here is I have two pressures with different levels of fluid. And I want to know which pressure is bigger or smaller. How does P1 relate to P2? If you want to think about this more like we drew it in class, it was like this. This would be the same situation. Where my liquid looks like that. Where my P1 would be on the left and P2 would be on the right. The figure's a little bit different. All right, let's stop at 45. 45. Awesome. B is right. P1, the pressure on this side, this has the lower level, so it's pushing that fluid up, and it goes up into the other side. This is the small pressure, this is the bigger pressure. This is like if you're at a restaurant, and you have a straw, and you put your mouth on the straw. You put your mouth on the straw, and you do what? You drink in, or what? No, you blow bubbles. You know what I'm talking about? You put the high pressure, and then it blows bubbles up into the soda. My wife always gets on to me when I do that. She's like, "Don't be such a kid." No, she doesn't say that. All right, let's answer this one on the right. On the left. 3 sources of pressure. What's the third source? Stop at 25. 25. What was that?
No.
Okay. Yeah, look at you. A is right. I think that was on the quiz. But look, we have 3 things that we've talked about. This is that pressure is equal to rho times G times H. Remember, you have 100,000 newtons of force, and it's due to that big column that goes all the way up to the edge of space, to the edge of our atmosphere. That's P equal rho GH. This is a principle. What's it called? The external force principle? That's Pascal's principle. That's like we have in hydraulic lifts. And then the third is the molecular interactions within a fluid, and that is the... No, that's quasi. That's going to come up. That's the ideal gas law. Okay? The PV equals nRT. So it's the molecular interactions within a fluid. Then let's do this one on the right. Ideal gas law is, I'll give it to you there. What happens if you increase the temperature? So the volume, pressure, gas constant, or does nothing change? Let's stop at 34. Yeah, B is right. If I increase the temperature, the volume will not decrease. The pressure will increase. The gas constant is constant. It doesn't change. So the only one that's right is that the pressure will increase. And another answer that could be right is that the volume could decrease. That could be also correct if that was an option, but it's not. All right, my siren told me this joke. I think he was 10 when he told it to me. So you have to keep in mind that it's a boys' middle school joke. You ready? Not. Oh shoot! Oh no, I forgot it. I'll try to think of it. I'm sorry. We'll get you later. All right. So, fluids in motion. A study of this is called fluid dynamics. If you go to grad school, you'll probably see it in greater detail. Or some of you might have seen it already. You might have done it in some of your AMP classes. Some of the stuff that we'll see. And as I said, fluid includes all things that flow. And that includes both liquids and waters. I mean, liquids and gases. There are some things that can flow that we don't really think of as fluids. Have y'all ever heard of the pitch drop experiment? You ever seen this? Hey, you guys never go on YouTube, do you? You never watch YouTube? Are you serious? What do you watch? Netflix. It's the bane of our IT department because it seems like they're always trying to get more bandwidth so that students can watch their Netflix. And I always tell them, hey, why don't y'all just ban Netflix from the campus? Like, they could do that, you know. Yeah, they said, no, we could never do that. Let's watch it. It's kind of cool. The pitch drop experiment. So keep tuned. In 14 years, let's see, a lot of y'all are sort of early 20s, right? So in your mid 30s, we'll experience another drop in the pitch drop experiment. Huh? It's cool. Isn't it cool? It's just like a museum display. There's no scientific discovery out of it. But it's kind of cool to see this thing that looks like a solid, but it actually flows like a liquid. Just over a very long, long time. All right, we have three characteristics of fluid flow. Fluid flow is steady. That means that the velocity at a point does not change. Right, so if I have fluid, I'm going to use lines to represent sort of the direction of the fluid flow. If I have a certain point, say right here, that particular point, V is constant. Now we'll see a little bit later, that doesn't mean that V here is the same as it is over here. It can be different at different points, but at a particular point, the speed, the velocity, is always going to be the same. If the velocity of the fluid there is 2 meters per second, in an ideal fluid, it will always be 2 meters per second. Fluid flow can be rotational or irrotational. And I'm sorry, I really should have three characteristics of ideal fluid flow here. So fluids flowing can either be steady or unsteady. But in the fluids we'll be talking about, which are an ideal case of fluid flow, we always consider steady flow. And, you know, steady flow is not uncommon. When you have water flowing in a garden hose, that's steady flow. Or when you have something flowing through a pipeline over many miles, that's steady flow. Even within our body, that often, as blood moves through our vessels, that's steady flow as well. Not in your heart. It's not ideal in your heart. Lots of stuff going on in your heart. Rotational or irrotational. For ideal fluid flow, it's irrotational, and that means that the fluid doesn't rotate. So you can probably think of some places where the fluid rotates, right? Where does the fluid rotate? Nobody ever says this. Is it embarrassing? The toilets. I know, but the fluid rotates, so that's rotational flow. So you go to the bathroom and say, hey, this isn't ideal. It's not ideal fluid flow because it's not irrotational. So it needs to just not rotate. Viscous or non-viscous? Viscosity describes the friction between molecules. And in ideal fluid flow, we'll be talking about non-viscous. Viscous fluids, well, what's more viscous, maple syrup or water? Right, so you get the idea. Viscous fluids are stickier. They stick together more. Right? Blood is a viscous fluid. And so we'll have to think more about blood when we get to that. That's where the plus equation comes in, because it helps us when we have a viscous fluid to think about the flow of it. So the viscosity describes the friction between molecules. And we're looking for non-viscous. And then also ideal fluid flow, the fluid is incompressible. That is, when you apply pressure, the volume stays the same. Look, I'll put some air in my hand right here. Put some air in my hand. So now I have air inside of this little cup. And then if I squish down on it, I still keep the air in it, but I change the volume. Is it compressible or incompressible? It's compressible, right? Because I can change the volume of it, but I still keep the same amount. But if I try to put water in my hand and do that, then it wouldn't work, right? Because I can't compress water. You ever do that at the pool? Where you say, hey, look, there's a crawdad in here? And then your little kids that gullible, they come over and look in the hole trying to see the crawfish, and then what do? And you go, and it squirts water from their eyes? They fall for it every time. And then laminar versus turbulent. In a laminar, the fluid flows in parallel layers. In a laminar flow, we're looking at, laminar is going to be our ideal situation. The fluid flows in parallel layers with no interaction between the layers. So if I think about breaking my fluid flow into pieces like that, I think of these laminates, right, where I have these different parts of the fluid flowing, and they don't intermingle, they don't come together. Because if they intermingled, then that would involve rotation, right? Like if this one went over to here, it would rotate around. But in laminar flow, they don't interact. The layers near to the sides of the pipe move more slowly. So if I'm thinking about my pipe, this is my pipe, I'm going to have slow speed over here and faster speed over here. That's okay. It's still steady because the speed is constant here and it's constant here. They're just different. And why does it move slower when it's closer to the edge? Yeah, it just sticks to the side of the pipe more friction. So similar to why if I shuffle my feet, that's slower than if I run or whatever. This usually occurs for viscous fluids at low speeds. And most blood flow is laminar, except for in the heart. In turbulent, these layers interact unpredictably. The velocity of the fluid changes a lot. changes. And sometimes blood flow is turbulent. Usually, and it's just when it's in the blood vessels, it's laminar. But sometimes blood flow is turbulent, like in the heart, when it contracts. And when it contracts, blood rushes quickly into the other chambers. And this causes a distinctive... All right, what's the sound? I've never actually heard it. What's it called? Love and duck. Can you make the sound? Anybody? Okay. Anyway, that's the turbulence in the heart. Right? It's not laminar flow, it's turbulent flow. We'll talk about the heart in a bit. Let's try these clicker questions. Which of these is not a characteristic of ideal fluid flow? The one on the left. All right, stop at 33. 33. Oh, y'all are awesome. It's easy when you've just seen it, right? It's just when you have to put everything away. But with practice, that comes. Laminar, irrotational, steady, and non-viscous, right? All of those are characteristics of ideal fluid flow. Knock, knock. Smell mop. No, thank you. Again, middle school joke, 5th grade, boy. Yeah. All right, let's try the one on the right. Liquids are what? Gases are what? Stop at 23. 23. The test, when we have it, it'll be about 50 questions long, but a good number of the questions will be like that you'll be able to do in 10 seconds, just as quickly as you can read them. Some of them will be a little more complicated. You'll have to think about them more, but usually students are able to finish in under an hour. Some students will be done in 30 minutes. C is right. Liquids are incompressible. Gases are compressible. All right, let's look at the flow rate. Oh, sorry. Generally, anytime we talk about a rate, we mean how something changes with time. And that's true for flow rate as well. Although flow rate refers to how the flow of fluid changes with time. And the mathematical definition is that Q, that's what we're going to use for flow rate, is Q, and it's going to be equal to volume divided by time. So sometimes you'll hear flow rate, not just flow rate, but you'll hear volume flow rate. That means that a certain volume of liquid is moving through space at a certain rate. And so in a pipe, for example, well, Q is equal to V divided by T. And in a pipe, the flow rate must be the same in different parts of the pipe. So if I have a pipe, for example, and I'm getting 10 cubic feet per second of flow rate down here, if I have another part of the pipe down here, I have to still be getting 10 cubic feet per second right there. Okay? So I have the same volume of liquid that's moving through at the same rate. And the reason for that is that you assume that you're not losing anything. In fact, if I had 8 cubic feet per second over here, then I would say I have a problem where I'm losing those other 2 cubic feet per second. Now we'll see that the velocity can change. That's different from the velocity. That we'll see a little bit later that the velocity can be bigger or smaller in the second part, but you're still going to get the same flow rate. How could that be? Like, how could I have it be a bigger velocity, but still get the same flow rate through this pipe? Yes. So if you change the shape of the pipe, and if I wanted to get a bigger velocity, how would I change the shape of the pipe? Would I make it bigger or smaller? Right, I make it smaller. You do that all the time. You ever used a water hose and you put your thumb over the end? That's what you do. You make the shape of the pipe smaller, that it keeps the same flow rate because you're not losing water anywhere, but it makes it go a lot faster. We'll see that. That's called the continuity equation. Oh, we'll see it right now, actually. The flow rate equation, this is sometimes called the continuity equation, or the equation of continuity. It just says that the flow rate Q1 has to be equal to Q2 at some other point in a pipe, where Q1 and Q2 would be like here or here. That they have to be the same. Otherwise, if they're different, that means I'm losing liquid somewhere. So Q1 has to equal to Q2. And since Q1 is V1 over T, and Q2 is V2 over T, volume over time. And I don't remember, but we can also say that volume in general is equal to area times some distance. You remember we talked about this earlier when we were talking about pressure? So if I want to know the volume of a cylinder, for example, I take the area of the circle on the top of that cylinder, which is pi r squared, and then multiply that times the height. Or if I want to know the volume of a rectangular prism, I multiply the length times width times the height of that rectangular prism. And so if I substitute that in, I get area 1 times d over t is equal to area 2 times d over t. And if you notice here, this distance over time, both of these are equivalent to speed. And so that's where the continuity equation comes from. Continuity equation is that A1, the area of my pipe, times V1, the speed of the liquid in the pipe, is equal to A2 times V2. This is area, this is speed, and we can think about a pipe where it changes shape, like that. Here I have an area that's relatively big. I'll call this A1. And I don't know, let's say that it's, 2 square meters. That's a pretty big pipe. And let's say that the velocity inside of here is equal to 3 meters per second. That means that I get, this is V1, that my flow rate here, Q1, is equal to A1 V1. It's equal to 6 cubic meters per second. So that's a question I could ask you, just given this pipe with this flow rate, with this area, this cross-sectional area, what is the flow rate? And it's you just multiply the two. You can see that by dimensional analysis, right? That I know that my flow rate is a volume per time, and a meter squared, if I multiply that times meters per second, then I get a volume per time in my units. Meter squared times meters per second is meters cubed per second. Now, what if the area down here is 1 square meter? What then is the velocity here? What is V2 equal to? We'll do it as a clicker question. Let's see. All right, what is the velocity in that second part of the pipe? Is it 3 meters per second? It's the same. 6 meters per second or 1.5 meters per second? What's the velocity of the new section of pipe? What's the velocity here? Over here it's 3 meters per second. I have 2 square meters. Over here it's 1 square meter, and I want to know what is the velocity of the water or the liquid in that second section of pipe. All right, let's stop at 50. Okay, look, on my test often you can just look at the question and not even really have to do any math, but if you just look at the numbers and think about which ones are reasonable. Because in this one there's really only one reasonable answer. The reason there's only one reasonable answer is because when I make the area smaller, that means that my speed must do what? Increase, decrease, or stay the same? If I make the area smaller, in order to keep the same flow rate, the same volume flow rate, I have to go faster. Because I'm getting 6 cubic meters per second through this pipe whether I want it or not. Here, it can just lumber along at 3 meters per second. But over here, where I have less area, it has to move faster in order to get 6 cubic meters per second passing a point every second. So I know that my speed has to be more than 3 meters per second. And I can just stop right there because there's only one option that's more, and that's B, 6 meters per second. But if I had two that were more, the way I would figure it out is I would say A1, V1, using this equation right here, A1, that's 2 square meters, right here, times V1, which is 3 meters per second, is equal to A2, that's 1 square meter, times V2. And then I would solve that for V2, and I would find that V2 is equal to 6. Okay? It's a good test question. Make sure you can do stuff like that regarding the flow rate. Flow rate's kind of important for us to do. What's next? I think we have another similar example on the next page. So here I have a pipe that has a cross-sectional area of 20 square centimeters. Water flows at 30 centimeters per second. What is the flow rate? Well, I would do what? I have the area and I have the speed. I just multiply those two. So I have my flow rate is equal to volume over time. But remember, this is also equal to the area times the velocity, A times V. And so that's equal to 20 square centimeters times 30 centimeters per second. And that's equal to 600 cubic centimeters per second, or cc's. That's what a cc is a cubic centimeter. A cc is about this much volume. 1 centimeter by 1 centimeter by 1 centimeter. And a centimeter is about the width of your pinky. Do you know that? It's true. So that's my volume flow rate. And then if my pipe goes to 10 square centimeters, what's going to happen to my speed? Well, my speed was 30 centimeters per second. And I'm making my pipe bigger or smaller now? Making it smaller by a factor of 2. If it gets smaller, is the speed going to go up or down? It's going to go up. It has to go faster through a smaller pipe. Like putting your finger over the end of the hose. And so what's going to be the new speed? Y'all are amazing. It's going to be 60. Right, because the area goes down, and so the speed goes up. Let me show you how we would do that there. I would say A1 V1 is equal to A2 V2. That is 20 times 30. That's this and this is equal to 10 centimeters squared times V2. 20 times 30, that's 600. And then I divide both sides by 10, which would be 60 centimeters per second. Now, what system of measurement have we been using? This is the SI system, but particularly, what is it? Yeah. Then we had the MKS, and then we had what else? CGS, right? Centimeters, grams, second. Don't forget your chapter 0 for the upcoming exam too. That'll be on there, even though we haven't had a reading quiz on it. Have a great day. Oh, the answer was V2 equals 60 centimeters per second. Isn't that right? Yes.
If we divide by 10.
Yeah, you divide by 10. So this is 600 equals 10 V2. Divide both sides by 10. A second.